close your eyes and imagine floating in the quietest place you have ever known. Now picture, far in the distance, a circle of absolute darkness against the starfield. No light escapes from it, no signal returns. It is a black hole. Tonight we are going to do something no human has ever done. We are going to descend into one. Not quickly, not recklessly, but slowly and calmly, following the mathematics step by step. We will orbit it first, watching space-time warp around us as we circle from a safe distance. Then we will approach, drifting closer to the event horizon where time begins to stretch like warm glass. We will cross that invisible boundary and enter a region from which nothing can return. Inside, the geometry of space and time will twist in ways that challenge every intuition you have. And at the very center, if the mathematics is to be believed, something extraordinary waits. A point of infinite density. A place where the known laws of physics break down completely. This is not science fiction. Every step of this journey is grounded in equations that have been tested and confirmed. General relativity, Einstein's masterwork from 1915, describes gravity as the curvature of space-time caused by mass and energy. Its predictions have been verified by over a century of experiments, from clocks on airplanes to gravitational wave detectors. The black hole solutions to Einstein's equations were first found by Carl Schwarzschild in 1916. He derived them while serving as a soldier on the Eastern Front of World War I, just weeks after Einstein published his theory. His solution describes the simplest possible black hole, one that does not spin and carries no electric charge. It predicts a boundary called the event horizon, and beyond it, a singularity at the center. Let us begin our descent. The stars are steady around us, and the mathematics will be our guide. We begin far from the black hole, at a distance of perhaps 1,000 Schwarzschild radii. The Schwarzschild radius is the size of the event horizon for a non-rotating black hole. For a black hole with 10 times the mass of our Sun, the Schwarzschild radius is about 30 kilometers. At our current distance, we are roughly 30,000 kilometers away from the center. From here, the black hole looks like a dark circle against the stars, surrounded by a thin ring of bent starlight. This ring is caused by gravitational lensing, the bending of light by curved space-time. Photons from stars behind the black hole are deflected around it, creating a halo of warped images. Arthur Eddington first confirmed that gravity bends light during a solar eclipse in 1919, making Einstein famous overnight. Near a black hole, the bending is far more extreme than anything Eddington measured near our Sun. Stars behind the black hole appear as thin arcs, stretched and distorted by the intense curvature of space-time. We can even see stars that should be directly behind the black hole, their light bent around and redirected toward us. At this distance, our clocks are still ticking at nearly the same rate as clocks far from any massive object. The gravitational time dilation here is negligible, perhaps a few parts per million slower than flat space-time. But as we move closer, that will change. Time will begin to slow. The term black hole was coined by the physicist John Archibald Wheeler in 1967, though the concept had existed for decades. Before Wheeler gave it that evocative name, these objects were often called frozen stars or collapsed stars. Wheeler understood that the name mattered. A good name can make a difficult idea accessible to everyone. The idea itself goes back even further. In 1783, the English clergyman John Michell imagined a star so massive that light could not escape from it. Pierre-Simon Laplace independently proposed the same idea in 1796, calling them dark stars. But it took Einstein's general relativity to provide the correct mathematical description of how such objects actually work. We have drifted closer now. Our orbit has tightened to roughly 100 Schwarzschild radii. At this distance, gravitational effects are becoming measurable, though still small. Our clocks are now running about 0.5% slower than clocks in flat space-time far from any mass. 0.5% may sound trivial, but it is thousands of times larger than the time dilation GPS satellites experience near Earth. We can see the accretion disk now, a vast, swirling structure of superheated gas orbiting the black hole. Not all black holes have accretion disks. They form only when enough matter falls inward and collects into orbit. The gas in the accretion disk is heated by friction and compression to millions of degrees. It glows brilliantly in X-rays and visible light, making the black hole's surroundings paradoxically among the brightest objects in the universe. The first image of a black hole was captured by the Event Horizon Telescope collaboration and released in April 2019. It showed the supermassive black hole at the center of galaxy Messier 87, known as M87 star. The image revealed a bright ring of emission surrounding a dark central shadow, exactly as general relativity predicted. In May 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the black hole at the center of our own Milky Way galaxy. Sagittarius A star has a mass of about 4 million times that of our Sun, compressed into a region smaller than Mercury's orbit. The light from the accretion disk is affected by the black hole's gravity in a phenomenon called gravitational redshift. Photons climbing out of the gravitational well lose energy, and their wavelength stretches toward the red end of the spectrum. As we study this black hole from our orbit, we notice something remarkable about its simplicity. A black hole, no matter how complex the star that created it, is described by only 3 numbers: its mass, its electric charge, and its spin, nothing else. This is called the no-hair theorem, a phrase coined by John Wheeler to express how featureless black holes are. All the information about the star that collapsed, its chemical composition, its shape, its history, is lost behind the event horizon. 2 black holes with the same mass, charge, and spin are identical, no matter what formed them. A black hole made from a collapsing star and one made from compressed hydrogen gas would be indistinguishable. The no-hair theorem was proved mathematically by a series of physicists in the 1960s and 1970s, including Vern Israel, Brandon Carter, and Stephen Hawking. It tells us that the event horizon is perfectly smooth, featureless, carrying no bumps, ridges, or markings of any kind. This extraordinary simplicity is part of what makes black holes so beautiful and so strange. In practice, most astrophysical black holes have negligible electric charge, so they are described by just 2 numbers, mass and spin. The solution for a spinning black hole was found by the New Zealand mathematician Roy Kerr in 1963. The Kerr solution is more complex than Schwarzschild's, but it is still exact, still beautiful, and still one of the most important results in general relativity. We are closer now, perhaps 10 Schwarzschild radii from the center, roughly 300 kilometers from our 10 solar mass black hole. Time dilation is becoming significant. Our clocks are running about 5% slower than clocks in flat space-time. If we could communicate with someone far away, they would hear our voices slightly lower in pitch, our words slightly stretched. The light from the accretion disk around us is separating into 2 distinct views. On one side, the disk appears brighter because matter is moving toward us, its light blue shifted by the Doppler effect. On the other side, the disk appears dimmer, its light red shifted as matter moves away. This asymmetry was visible in the Event Horizon Telescope image of M87 star, where one side of the ring was noticeably brighter than the other. The tidal forces are growing stronger now. Tidal forces arise because gravity is not uniform across space. The parts of our spacecraft closer to the black hole feel a stronger gravitational pull than the parts further away. This difference in pull stretches objects vertically and compresses them horizontally, an effect called tidal stretching. For a stellar mass black hole, the tidal forces become dangerously strong well outside the event horizon. For a supermassive black hole, millions or billions of solar masses, the tidal forces at the event horizon are surprisingly gentle. This is because the event horizon of a supermassive black hole is enormously large, and gravity changes more gradually across it. An astronaut falling into a supermassive black hole might not feel anything unusual at the moment of crossing the event horizon. This counterintuitive fact was noted by Robert Oppenheimer and Hartland Snyder in their landmark 1939 paper on gravitational collapse. They showed that a sufficiently massive star could collapse beyond the point of no return, forming what we now call a black hole. At 1.5 Schwarzschild radii, we encounter a remarkable boundary called the photon sphere. At this precise distance, gravity is strong enough to bend light into circular orbits around the black hole. A photon emitted tangentially at this radius will orbit the black hole indefinitely, circling forever in a perfect loop. In practice, these orbits are unstable. The slightest perturbation sends the photon either spiraling inward or escaping outward. But the existence of the photon sphere has a startling consequence for what we would see. If we looked straight ahead at this radius, we could theoretically see the back of our own head. Light from behind us would travel all the way around the black hole and return to our eyes. This is not a trick of optics. It is a direct consequence of the extreme curvature of space-time at this radius. The photon sphere is the innermost orbit at which anything can circle the black hole without falling in, and only light can do it. Below the photon sphere, no stable orbits exist for any object, no matter how fast it moves. The innermost stable circular orbit for a massive object is at 3 Schwarzschild radii for a non-rotating black hole. This is called the ISCO, and it marks the inner edge of the accretion disk. Inside the ISCO, matter spirals inward rapidly, falling toward the event horizon with no possibility of sustained orbit. Time at the photon sphere runs at about 58% of its rate in flat spacetime, a dramatic slowing. We continue our descent. The event horizon lies just ahead. At twice the Schwarzschild radius, our clocks run at about 71% of flat spacetime rate. At 1.5 times the Schwarzschild radius, about 58%. At 1.1 times, about 30%. The closer we get, the more dramatically time slows from the perspective of any distant observer watching us. If someone far away could watch us through a powerful telescope, they would see our movements becoming slower and slower. Our skin would appear to shift in color, reddening as the light we emit is gravitationally red-shifted. We would appear to dim, our image fading like a photograph left in the sun. To the distant observer, we would never quite reach the horizon. We would appear to freeze, asymptotically approaching it forever. This is why black holes were once called frozen stars. From outside, nothing ever appears to cross the horizon. But from our own perspective, falling inward, nothing unusual happens at the moment of crossing. We pass through the event horizon in a finite amount of our own time, feeling no barrier, no wall, no sudden change. The event horizon is not a physical surface. It is a mathematical boundary in space-time. It is defined as the boundary of the region from which no signal can ever reach a distant observer, no matter how long one waits. The radius of the event horizon for a Schwarzschild black hole is given by the formula 2gm over c squared. G is Newton's gravitational constant, m is the mass of the black hole, and c is the speed of light. For our 10 solar mass black hole, this gives an event horizon radius of about 30 kilometers. The event horizon of the supermassive black hole Sagittarius A star is about 12 million kilometers across, roughly 17 times the diameter of our Sun. Despite its enormous size, Sagittarius A star is invisible in ordinary light. We detect it only through its gravitational effects on nearby stars. The GRAVITY instrument at the European Southern Observatory's Very Large Telescope tracked stars orbiting Sagittarius A star and confirmed gravitational redshift near it. The star called S2 passes within about 120 astronomical units of the black hole, close enough to experience measurable time dilation. We are at the event horizon now. This is the point of no return. From outside, a distant observer would say our clocks have stopped entirely. The rate of time here, as seen from far away, is 0. But we feel nothing. Our heartbeats continue. Our thoughts flow normally. Our clocks tick steadily. This is one of the most profound aspects of general relativity. Time is not universal. It is local and personal. What is infinite from one perspective is perfectly finite from another. We have crossed an invisible line in space-time. Behind us, the universe we came from is now causally disconnected. No signal we send, no light we emit, no gravitational wave we create can ever reach the outside again. We can still receive signals from outside. light from the distant universe can still reach us, falling inward alongside us. But we cannot respond. We are inside a one-way membrane in space-time. Roger Penrose explored the geometry of black hole interiors with extraordinary rigor, beginning in the 1960s. In 1965, he proved a theorem showing that once matter crosses the event horizon, it must inevitably reach the singularity. This is the Penrose singularity theorem, one of the most important results in mathematical physics. Penrose was awarded the Nobel Prize in Physics in 2020 for this work, more than 50 years after the original proof. His theorem does not tell us what happens at the singularity, only that reaching it is inevitable once you are inside. Inside the event horizon, the roles of space and time undergo a remarkable transformation. In the Schwarzschild metric, the radial coordinate and the time coordinate effectively swap their mathematical character. Outside the horizon, you can choose to move forward or backward in space, but you are compelled to move forward in time. Inside the horizon, you can choose to move forward or backward in time, but you are compelled to move inward in space. Moving toward the singularity is no longer a matter of direction. It is a matter of time. The singularity is not a place. It is a moment in your future. This is perhaps the most mind-bending consequence of crossing the event horizon. We are inside the black hole now. The stars we left behind are visible above us, but their light is increasingly blue-shifted. Light falling inward alongside us gains energy as it falls deeper into the gravitational well. The universe above appears to compress into a shrinking circle of light, an effect of the extreme space-time curvature. This circle will continue to shrink as we fall further inward, eventually becoming a single brilliant point. Around us, the geometry of space is no longer what our intuition expects. In ordinary flat space-time, 3 dimensions of space stretch out equally in all directions. Inside the black hole, the radial direction is fundamentally different from the other two. Moving inward is not like moving left or right. It is like moving forward in time, unstoppable and irreversible. The Chandrasekhar limit, discovered by Subramanian Chandrasekhar in the 1930s, sets the maximum mass of a white dwarf star at about 1.4 solar masses. Above this limit, electron degeneracy pressure cannot prevent further collapse, and the star's core compresses to a neutron star, or, if massive enough, a black hole. The collapse that forms a stellar black hole happens in less than a second after the core exceeds the maximum mass for a neutron star. The first observational evidence for black holes came from X-ray binary systems, where a compact object pulls matter from a companion star. Cygnus X1, discovered in 1964, was the first widely accepted black hole candidate, with a mass of about 15 solar masses. The matter spiraling into Cygnus X1 creates intense X-ray emission as it heats to millions of degrees in the accretion disk. As we continue falling inward, the tidal forces are growing. The difference in gravitational pull between our head and our feet increases. The stretching effect of tidal forces near a black hole has been given a vivid name: spaghettification. The term was popularized by Stephen Hawking in his book A Brief History of Time, published in 1988. Spaghettification occurs because gravity pulls more strongly on the parts of an object closer to the center of mass. For a stellar mass black hole, spaghettification would be lethal well before the event horizon. An astronaut falling feet first would be stretched vertically and compressed horizontally into a thin strand. For our 10 solar mass black hole, the tidal forces at the event horizon are roughly 100 billion times Earth's gravity per meter of separation. No material, no structure, no arrangement of atoms could survive such forces. But for a supermassive black hole, the tidal forces at the horizon can be surprisingly mild. For a black hole of 4 million solar masses like Sagittarius A star, the tidal forces at the horizon are about the same as what you feel standing on Earth. For a black hole of 1 billion solar masses, the tidal forces at the horizon would be less than the gravity on the Moon. This means an astronaut could cross the event horizon of a sufficiently massive black hole without being torn apart. They would not even know they had crossed it until they tried to leave and found they could not. The spaghettification would come later, as they fell deeper and the curvature increased. Eventually, no matter how large the black hole, the tidal forces become overwhelming as the singularity approaches. Every atom is pulled apart, every bond is broken, the object is stretched into a stream of particles falling toward the center. In 1974, Stephen Hawking made one of the most surprising discoveries in theoretical physics. He showed that black holes are not perfectly black, they emit a faint glow of thermal radiation. This radiation, now called Hawking radiation, arises from the quantum mechanical properties of the vacuum near the event horizon. In quantum field theory, the vacuum is not truly empty. It is a seething foam of virtual particle-antiparticle pairs constantly popping into and out of existence. Near the event horizon, one member of a virtual pair can fall into the black hole while the other escapes. The escaping particle carries real energy away from the black hole, while the infalling particle effectively carries negative energy inward. The net effect is that the black hole slowly loses mass, radiating energy as if it had a temperature. The temperature of a black hole is inversely proportional to its mass. Small black holes are hot, large ones are cold. For a black hole of 10 solar masses, the Hawking temperature is about 0.6 Kelvin, far colder than the cosmic microwave background. This means that stellar mass black holes are actually absorbing more energy from their surroundings than they radiate, so they are currently growing, not shrinking. But in the far future, when the universe has cooled below even this tiny temperature, black holes will begin to evaporate. The evaporation time for a 10 solar mass black hole is approximately 10 to the 68th years, an unimaginably long time. For comparison, the current age of the universe is only about 1.4 times 10 to the 10th years. As a black hole evaporates, it gets smaller and hotter, radiating more and more intensely. In the final moments of evaporation, the black hole would release a burst of energy in a flash of high-energy particles and gamma rays. Hawking's discovery connected three previously separate areas of physics: general relativity, quantum mechanics, and thermodynamics. It was one of the first results to hint at how a theory of quantum gravity might work, though we still do not have such a theory. Before Hawking's work, the Israeli physicist Jacob Bekenstein proposed in 1972 that black holes have entropy. Entropy is a measure of disorder, of the number of microscopic arrangements consistent with a system's macroscopic properties. Bekenstein argued that when matter falls into a black hole, its entropy does not disappear. Instead, the black hole's own entropy increases. He proposed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was remarkable. In ordinary physics, the entropy of a system scales with its volume. For black holes, it scales with the area of the boundary. Hawking's calculation of black hole radiation confirmed Bekenstein's intuition and pinned down the precise proportionality constant. The Bekenstein-Hawking entropy formula states that the entropy equals 1/4 of the horizon area, measured in Planck units. One Planck area is approximately 10 to the minus 65 square centimeters, an almost inconceivably small unit. For a solar mass black hole, the Bekenstein-Hawking entropy is about 10 to the 77, an astronomically large number. This is far larger than the entropy of the star that collapsed to form the black hole, suggesting that black holes are the most entropic objects in the universe. The fact that entropy scales with area, not volume, was the first major clue toward what would become the holographic principle. Hawking radiation created a profound puzzle known as the black hole information paradox. In quantum mechanics, information is never destroyed. The evolution of a quantum system is always reversible, at least in principle. If you know the complete quantum state of a system at one time, you can calculate its state at any other time, past or future. But if a black hole forms and then evaporates away completely, what happens to the information that fell into it? The Hawking radiation appears to be perfectly thermal, carrying no information about what formed the black hole. A black hole formed from a collapsed star, and one formed from compressed books, would emit the same featureless radiation. If the black hole evaporates completely and all that remains is this featureless radiation, then the information has been destroyed. This contradicts a fundamental principle of quantum mechanics called unitarity. Hawking initially argued that information is genuinely lost in black holes, that quantum mechanics must be modified. Then, as Susskind and Gerard Hooft disagreed, they argued that the information must somehow be preserved. In the 1990s, Susskind and Hooft developed the holographic principle, which proposes that all information about the interior of a black hole is encoded on its event horizon. The holographic principle suggests that the three-dimensional interior of a black hole is fully described by the two-dimensional surface at its boundary. This is analogous to a hologram, where a flat surface contains all the information needed to reconstruct a three-dimensional image. The holographic principle has profound implications far beyond black holes. It suggests that the entire universe may be a holographic projection from a lower dimensional boundary. In 1997, the Argentine-American physicist Juan Maldacena provided strong mathematical evidence for the holographic principle. His ADS-ECFT correspondence showed that a gravitational theory in a certain type of curved space-time is mathematically equivalent to a non-gravitational quantum theory on its boundary. This was a monumental result. It means that gravity itself might be an emergent phenomenon, arising from more fundamental quantum interactions. In 2004, Hawking conceded a famous bet with John Preskill, acknowledging that information is likely preserved in black hole evaporation. But exactly how the information gets out remains one of the deepest unsolved problems in theoretical physics. In 2012, a group of physicists sharpened the information paradox into an even more dramatic form. Ahmed Al-Mehri, Donald Maroff, Joseph Polchinski, and James Sully published a paper arguing for a startling conclusion. They showed that three widely accepted principles of physics cannot all be true simultaneously near a black hole. The three principles are unitarity, which says information is preserved; the equivalence principle, which says free fall feels like floating; and the assumption that physics far from the black hole is normal. If information is preserved, they argued, then the event horizon cannot be a smooth, unremarkable boundary. Instead, an infalling observer might encounter a wall of high-energy particles at the horizon, a firewall. This would violate the equivalence principle, one of the foundational pillars of general relativity. The firewall paradox, often called the AMPS paradox after its authors, sparked intense debate in the physics community. Some physicists accepted the firewall as real. Others argued that the equivalence principle must be preserved at all costs. Susskind and Maldacena proposed a radical resolution called ER equals EPR, linking wormholes to quantum entanglement. The debate continues today. No consensus has been reached, and the firewall paradox remains one of the most active areas of research in theoretical physics. To understand the geometry inside a black hole, physicists use a tool called a Penrose diagram. Named after Roger Penrose, these diagrams compress the infinite expanse of spacetime into a finite, diamond-shaped picture. In a Penrose diagram, light always travels at 45-degree angles, making it easy to see which events can influence which others. For a Schwarzschild black hole, the Penrose diagram reveals that the singularity is not a point in space, but a space-like surface in the future. Once inside the horizon, every possible future path leads to the singularity, just as every path in ordinary spacetime leads forward in time. The Penrose diagram also shows that a complete Schwarzschild oscillation technically contains two universes connected by a bridge. This bridge is sometimes called an Einstein-Rosen bridge or a wormhole, first described by Einstein and Nathan Rosen in 1935. However, this wormhole is not traversable. It pinches off too quickly for anything, even light, to pass through. The idea of traversable wormholes has been explored by physicists like Kip Thorne, but would require exotic matter with negative energy density. For a rotating Kerr black hole, the Penrose diagram is richer. It contains an infinite chain of connected universes. In the idealized Kerr solution, an infalling observer could pass through the singularity and emerge into a different universe. But most physicists believe this idealized picture does not survive in realistic conditions. Perturbations would destroy the inner structure. The mathematician Demetrios Christodoulou and others have shown that the inner Cauchy horizon of a Kerr black hole is unstable. Even tiny perturbations such as a single photon falling in would cause the Cauchy horizon to become singular. Most real black holes are not described by Schwarzschild solution, they spin. When a star collapses, it carries its angular momentum with it. The resulting black hole inherits that spin. The Kerr metric, published by Roy Kerr in 1963, describes the spacetime around a rotating black hole. A spinning black hole has a fascinating feature that Schwarzschild solution lacks: the ergosphere. The ergosphere is a region outside the event horizon where spacetime is dragged around by the black hole's rotation. Inside the ergosphere, it is impossible to remain stationary relative to distant stars. You are forced to rotate with the black hole. Roger Penrose realized in 1969 that the ergosphere allows energy to be extracted from a rotating black hole. In the Penrose process, an object enters the ergosphere and splits into two parts. One falls into the black hole with negative energy, the other escapes with more energy than the original object had. This is not a violation of energy conservation. The escaping piece gains energy at the expense of the black hole's rotational energy. The black hole slows down slightly with each extraction, and the process can continue until all rotational energy is removed. A maximally spinning Kerr black hole stores up to 29% of its total mass energy as rotational energy. The Blandford-Zenejek process, described in 1977, is a more realistic mechanism for extracting energy from spinning black holes through magnetic fields. It is thought to power the enormous jets of plasma observed shooting from the centers of active galaxies, some extending millions of light-years into space. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. The signal came from two black holes, each about 30 solar masses, spiraling together and merging 1.3 billion light-years away. Gravitational waves are ripples in spacetime itself, predicted by Einstein in 1916, but not directly detected for nearly a century. When two black holes merge, the final moments produce the most violent events in the universe since the Big Bang. The gravitational wave signal from a merger carries a characteristic chirp, a rapidly rising frequency, as the black holes spiral faster and faster. The peak power emitted in gravitational waves during a merger briefly exceeds the combined light output of all the stars in the observable universe. LIGO detects these waves by measuring changes in the length of its 4-kilometer laser arms, smaller than 1/10,000th the diameter of a proton. Since the first detection, LIGO and its European partner Virgo have recorded nearly 100 gravitational wave events. Each event tells us about the masses, spins, and distances of the merging objects, opening an entirely new window on the universe. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish for the LIGO detection. In August 2017, LIGO and Virgo detected gravitational waves from two merging neutron stars, and telescopes worldwide saw the same event in light. This multi-messenger observation confirmed that gravitational waves travel at the speed of light, as Einstein predicted. For a rotating Kerr black hole, the interior structure is more complex than Schwarzschild solution. Inside the outer event horizon, there is a second boundary called the inner horizon, or Cauchy horizon. At the Cauchy horizon, something extraordinary is predicted to happen. The gravitational blue shift of infalling light becomes infinite. All the light that will ever fall into the black hole, for all of eternity, is compressed into a single instant at this boundary. An observer reaching the Cauchy horizon would theoretically see the entire future history of the external universe flash before them in an instant. In practice, this infinite concentration of energy is thought to destroy the Cauchy horizon through a phenomenon called mass inflation. Mass inflation was described by Eric Poisson and Werner Israel in 1990, showing that the inner horizon is generically unstable. The curvature grows without bound near the inner horizon, converting it into a null singularity. This means the neat, orderly picture of a Kerr black hole interior probably does not survive in reality. What actually happens inside a real rotating black hole remains one of the great unknowns in physics. Let us return to the simpler Schwarzschild case, a non-rotating black hole, and continue our descent toward the center. As we fall inward from the event horizon, the tidal forces grow rapidly. The curvature of spacetime increases as the inverse cube of the remaining distance to the singularity. Any extended object is stretched vertically and compressed horizontally with ever-increasing ferocity. Atoms are torn apart, nuclei are disrupted, even the fundamental particles themselves are subjected to unbounded gravitational forces. The Kretschmer scalar, a measure of the curvature of spacetime, diverges as we approach the center. This is not a coordinate artifact, not a trick of the mathematics. It is a genuine physical singularity in the geometry of spacetime. At the singularity itself, the curvature becomes infinite. The metric tensor, which describes the shape of spacetime, is undefined. The singularity of a Schwarzschild black hole is a space-like singularity, meaning it lies in the future of every observer inside the horizon. You cannot avoid it any more than you can avoid next Tuesday. The singularity is a moment in time, not a place in space. Penrose's singularity theorem of 1965 guarantees that singularities form under very general conditions, not just in perfectly symmetric cases. The theorem requires only that gravity is attractive, that there is enough matter to form a trapped surface, and that spacetime is not too pathological. These conditions are easily satisfied in the collapse of a massive star, confirming that singularities are a generic feature of general relativity. So what is the singularity? What actually exists at the center of a black hole? The honest answer, the answer that physicists will give you if pressed, is that we do not know. General relativity predicts that the singularity is a point, or in the Schwarzschild case a moment, of infinite density and infinite curvature. But infinite density is not a physical description. It is a mathematical statement that the theory has broken down. When a theory predicts infinity, it is usually telling us that we have pushed the theory beyond its domain of validity. General relativity is a classical theory. It does not include quantum effects. At the singularity, the curvature reaches the Planck scale, where quantum gravitational effects are expected to dominate. The Planck length is approximately 1.6 times 10 to the minus 35 meters, far smaller than any distance we can currently probe. The Planck time is about 5.4 times 10 to the minus 44 seconds, the shortest meaningful interval of time in physics as we understand it. At these scales, the smooth, continuous spacetime described by general relativity is expected to break down into something fundamentally different. What that something is, we do not yet know, but several proposals exist. The search for a theory of quantum gravity, a theory that unifies general relativity with quantum mechanics, is one of the greatest quests in modern physics. Several approaches have been developed over the past half-century, each offering different pictures of what might happen at the singularity. String theory proposes that the fundamental constituents of the universe are not point particles, but tiny vibrating strings. In string theory, the singularity might be resolved by the finite size of strings. A point of infinite density could be smoothed out. Loop quantum gravity, developed primarily by Abe Ashtekar, Carlo Rovelli and Lee Smolin, takes a different approach. It proposes that spacetime itself is quantized, made up of discrete chunks at the Planck scale, like a fabric woven from tiny loops. In loop quantum gravity, the singularity is replaced by a quantum bounce. Instead of collapsing to infinite density, matter rebounds. This bounce might connect the black hole interior to a new expanding region, perhaps even a baby universe. The idea that a black hole might give birth to a new universe is speculative but not easily dismissed. Lee Smolin has proposed that black holes create new universes with slightly different physical constants, a form of cosmological natural selection. Another approach, causal set theory, proposes that spacetime is fundamentally discrete, a collection of events connected by causal relationships. In all these approaches, the classical singularity of general relativity is expected to be modified or eliminated by quantum effects. But none of these theories has been tested experimentally. The energies required are far beyond anything we can achieve in a laboratory. Let us pause here, at the edge of what physics can currently describe, and reflect on what we have found. We descended from a distant orbit where the black hole was just a dark circle in the starfield. We passed through the photon sphere, where light itself orbits the black hole. We crossed the event horizon, the invisible boundary beyond which escape is impossible. Inside, we found that space and time have swapped their roles, and the singularity lies not ahead of us in space, but ahead of us in time. We explored Hawking radiation, which shows that black holes are not eternal. They slowly evaporate, returning their mass to the universe as featureless thermal radiation. We encountered the information paradox, perhaps the deepest puzzle in modern physics, asking whether information is destroyed inside a black hole. And we arrived at the singularity, where general relativity predicts infinite curvature, but where a quantum theory of gravity is needed to tell the true story. The singularity is not the end of the story. It is the beginning of a new chapter, one that physics has not yet written. What lies at the bottom of a black hole is, in the deepest sense, a question about the fundamental nature of space-time itself. Roger Penrose proposed in 1969 that nature might protect us from the consequences of singularities through a principle called cosmic censorship. The weak cosmic censorship conjecture states that singularities formed from realistic gravitational collapse are always hidden behind event horizons. In other words, naked singularities, singularities visible to the outside universe, do not form in nature. If cosmic censorship is true, then the breakdown of physics at the singularity is kept safely locked away from the rest of the universe. The universe protects itself from its own contradictions. Despite decades of effort, cosmic censorship has neither been proved nor disproved in full generality. Some special cases have been shown to violate it, but these typically involve unrealistic conditions like perfect symmetry or exotic matter. The strong cosmic censorship conjecture is more restrictive. It states that the interior of a black hole is generically singular, preventing passage to other universes. If strong cosmic censorship holds, then the idealized wormholes and alternate universes in the Kerr solution do not exist in reality. Nature, it seems, might be telling us that black hole interiors are simpler and more brutal than the mathematics allows in its most idealized forms. While we cannot observe the interior of a black hole directly, we have extraordinary observational evidence that black holes exist. The Event Horizon Telescope combined radio dishes across 6 continents to create an Earth-sized virtual telescope. It achieved an angular resolution fine enough to read a newspaper in New York from a cafe in Paris. The image of M87 star matched the predictions of general relativity with remarkable precision. The dark shadow at the center of the image corresponds to the photon capture region, closely related to the event horizon and photon sphere. The bright ring of the mission is light from hot gas near the black hole, gravitationally lensed into a ring. The asymmetry of the ring is due to relativistic beaming, the Doppler boosting of light from gas moving toward us. Sagittarius A star, our own galaxy's central black hole, was imaged in 2022, confirming similar predictions. LIGO's gravitational wave detections have confirmed that black holes merge exactly as general relativity predicts. The ring-down signal after a merger, when the newly formed black hole settles into its final state, matches the no-hair theorem precisely. The merged black hole vibrates at specific frequencies determined only by its mass and spin, shedding all other information. Every observation, every measurement, confirms general relativity's description of black holes from the outside. What remains unknown, tantalizing and profound, is what happens on the inside. The first rigorous mathematical description of gravitational collapse to a black hole was published in 1939. J. Robert Oppenheimer and Hartland Snyder showed that a sufficiently massive sphere of dust, collapsing under its own gravity, would form an event horizon. The calculation assumed a uniform, pressureless dust cloud with perfect spherical symmetry. Despite these simplifications, the essential physics was captured. A collapsing star can reach a point from which light cannot escape. The collapse as seen by a distant observer appears to slow down and freeze at the event horizon. But the infalling matter continues through the horizon and reaches the singularity in a finite time by its own clocks. Oppenheimer would go on to lead the Manhattan Project during World War II, and he never returned to black hole physics. His 1939 paper was largely forgotten for decades, overshadowed by the demands of war and nuclear physics. It was not until the 1960s, with the work of Penrose, Hawking, Wheeler and others, that black holes became a central topic in physics. The golden age of black hole physics, from roughly 1963 to 1975, produced many of the results we have discussed tonight. Black holes obey a set of laws that are formally identical to the laws of thermodynamics. The Zeroff law states that the surface gravity of a stationary black hole is constant across the event horizon, analogous to temperature being uniform in thermal equilibrium. The first law relates changes in mass, area, angular momentum and charge, analogous to the first law of thermodynamics relating energy, entropy, temperature, and work. The second law states that the area of the event horizon never decreases, just as the entropy of a closed system never decreases. This area theorem was proved by Stephen Hawking in 1971, and it was one of the results that inspired Bekenstein to propose that black holes carry entropy. The third law states that it is impossible to reduce the surface gravity to zero in a finite number of steps, analogous to the unattainability of absolute zero temperature. When Hawking discovered that black holes radiate thermally, the analogy became an identity. Black holes genuinely have temperature, they genuinely have entropy, they genuinely obey the laws of thermodynamics. This deep connection between gravity, quantum mechanics, and thermodynamics is one of the most beautiful results in all of physics. It hints that gravity, temperature, and information are fundamentally related in ways we are only beginning to understand. At the singularity, several foundational principles of physics break down simultaneously. General relativity itself fails. The theory predicts its own inadequacy at the point of infinite curvature. The smooth space-time manifold that general relativity describes ceases to exist at the singularity. Causality may break down. Inside a Kerr black hole, closed time-like curves, paths that loop back to the same event, are mathematically possible. If such paths exist, cause and effect would lose their usual meaning. You could, in principle, influence your own past. Most physicists believe that quantum gravity will prevent closed time-like curves from forming, but we cannot be certain. The concept of distance breaks down. Near the singularity, the curvature is so extreme that the notion of spatial separation becomes meaningless. The concept of time also breaks down. At the Schwarzschild singularity, the time coordinate reaches a maximum and simply ends. This is not like reaching the edge of a map where you can simply continue beyond the border. The singularity is the genuine end of time for any object that reaches it, at least within general relativity. Quantum mechanics, in its standard formulation, assumes a fixed background spacetime through which particles move. At the singularity, there is no background spacetime. Quantum mechanics as we know it cannot be applied. This is precisely why a theory of quantum gravity is needed. It must describe physics in regimes where both gravity and quantum effects are strong. The singularity is not a physical object. It is a signpost marking the boundary of our current understanding. Beyond it lies territory that physics has not yet mapped. What does it mean that the laws of physics break down at the center of a black hole? Some physicists see it as a failure of our theories, a sign that we need better mathematics. Others see it as a hint about the nature of reality itself, a suggestion that the universe has deeper structure than we have yet imagined. The physicist John Wheeler, who coined the term black hole, spent his later career exploring the idea that information and observation are fundamental to physics. He proposed the phrase "it from bit," suggesting that the physical world arises from information at the deepest level. If Wheeler was right, then the information paradox is not just a puzzle about black holes. It is a puzzle about the nature of existence. The holographic principle, if true, means that the three-dimensional world we experience is encoded on a two-dimensional boundary. This is profoundly counterintuitive. We feel solidly three-dimensional, yet the mathematics suggests otherwise. Black holes, by pushing physics to its extremes, have taught us more about the fundamental nature of space-time than perhaps any other object in the universe. They are laboratories for quantum gravity, even though we cannot visit them. In the far future of the universe, black holes will be among the last objects remaining. After all the stars have burned out, after all the galaxies have dispersed, black holes will endure. But even they are not eternal. Hawking radiation ensures that every black hole will eventually evaporate. A stellar mass black hole will take roughly 10 to the 67th years to evaporate, an almost incomprehensible span of time. The supermassive black holes at the centers of galaxies will take far longer, perhaps 10 to the 100th years. During this immense span, each black hole slowly shrinks, its temperature rising as it loses mass. In the final moments, the black hole becomes microscopically small and extraordinarily hot. The final evaporation happens in a flash, releasing the remaining mass energy in a burst of particles and radiation. After the last black hole has evaporated, the universe will be a thin soup of particles and radiation, slowly cooling toward absolute zero. This is the heat death of the universe, the state of maximum entropy, the ultimate equilibrium. Black holes, which began as the most concentrated objects in the universe, will end as the most diffuse radiation. There is a quiet poetry in this transformation, from infinite density to infinite diffusion, from the smallest point to the widest void. Let us gather what we have learned on this journey, calmly and clearly. We know that black holes exist. Their gravitational effects have been measured, their images captured, their mergers heard. We know that the event horizon is a one-way boundary in space-time, through which light and matter can enter but never leave. We know that the singularity, as predicted by general relativity, represents a breakdown of the theory at infinite curvature. We know that black holes radiate through Hawking radiation, connecting gravity to quantum mechanics and thermodynamics. We know that the information paradox challenges our understanding of how quantum mechanics and gravity coexist. We do not know what replaces the singularity when quantum gravity effects are included. We do not know whether information is truly preserved in black hole evaporation, or how it escapes if it is. We do not know whether the interior of a black hole connects to other regions of space-time, other universes, or simply ends. We do not yet have a theory of quantum gravity that can answer these questions. But we have clues: the holographic principle, the Bekenstein-Hawking entropy, the ADS/CFT correspondence, all point towards something deep. The answer to what lies at the bottom of a black hole is likely to be one of the most important discoveries in the history of physics. There is something deeply peaceful about reaching the edge of knowledge and simply sitting with it. We do not need to have all the answers tonight. The questions themselves are beautiful. What lies at the center of a black hole is one of the deepest mysteries the universe has to offer. And it is a mystery that connects the very large, the curvature of space-time across billions of light years, to the very small, the quantum structure of reality at the Planck scale. Einstein gave us the tools to ask the question. Schwarzschild, Kerr, Penrose, Hawking, Bekenstein, Susskind, and many others have sharpened it. The next generation of physicists may answer it, or perhaps the answer will require ideas that no one has yet imagined. For now, we can rest with the knowledge that the universe is stranger, deeper, and more beautiful than common experience suggests. A place where time stops, a boundary you can cross but never return from, a point where the laws of physics dissolve into mystery. These are real features of the universe we live in, confirmed by decades of observation and mathematical proof. And they are waiting quietly at the center of every black hole in the cosmos. A star spends most of its life in a delicate balance. The outward pressure from nuclear fusion in its core counteracts the inward pull of gravity. When the nuclear fuel is exhausted, this balance is broken. Gravity wins. For a star with a mass less than about 8 times that of our Sun, the collapse stops at the white dwarf stage. Electron degeneracy pressure, a quantum mechanical effect, supports the white dwarf against further collapse. Subrahmanyan Chandrasekhar showed in the 1930s that this support has a limit, about 1.4 solar masses. Above this Chandrasekhar limit, the core collapses further, and electrons are forced into protons, creating neutrons. The result is a neutron star, supported by neutron degeneracy pressure with a density of about 1 billion tons per teaspoon. But neutron degeneracy pressure also has a limit at roughly 2 to 3 solar masses. Above this Tolman-Oppenheimer-Volkoff limit, no known force can halt the collapse. The core continues to compress, passing through the event horizon and forming a singularity. The outer layers of the star are blown away in a supernova explosion, one of the most energetic events in the universe. The supernova briefly outshines an entire galaxy, while at its heart, a black hole is born. Some black holes form without a visible supernova through a process called direct collapse, where the star implodes quietly. Supermassive black holes, found at the centers of most galaxies, likely form through a combination of direct collapse, mergers, and accretion over billions of years. The gravitational time dilation near a black hole follows a precise mathematical formula derived from the Schwarzschild metric. The rate at which time passes, relative to a distant observer, is given by the square root of 1 minus the Schwarzschild radius, divided by the distance. At twice the Schwarzschild radius, this gives a time dilation factor of about 0.2707. Time runs at about 71% of its normal rate. At 1.5 times the Schwarzschild radius, the factor drops to about 0.577, or 58%. At 1.1 times the Schwarzschild radius, time runs at only about 30% of its distant rate. At 1.01 times the Schwarzschild radius, the factor is about 10%. Time has nearly stopped. At the horizon itself, the formula gives exactly zero. Time, as measured by a distant observer, does not pass at all. This is not an approximation or an idealization. It is the exact prediction of general relativity for a Schwarzschild black hole. For a rotating Kerr black hole, the formula is more complex, involving both the mass and the spin parameter. A rapidly spinning black hole can have an event horizon significantly smaller than a non-spinning one of the same mass. The extreme time dilation near black holes has been confirmed indirectly through observations of X-ray emission from accreting black holes. The iron K-alpha emission line, observed in X-rays from the inner accretion disk, is broadened and skewed by gravitational redshift and time dilation. These observations from telescopes like XMM Newton and NuSTAR confirm that the innermost regions of accretion disks experience severe time dilation. The holographic principle is perhaps the most radical idea to emerge from the study of black holes. It states that the maximum amount of information that can be contained in a region of space is proportional to the area of its boundary, not its volume. This was first suggested by 't Hooft in 1993 and given a precise form by Susskind in 1995. The Bekenstein-Hawking entropy formula for black holes is the prototype of this principle. A black hole's entropy, proportional to its horizon area, sets the maximum entropy for any region of that size. If you try to pack more information into the region than the black hole allows, the region would itself collapse into a black hole. This suggests that three-dimensional physics can always be described by a theory living on a two-dimensional surface. Maldaceno's ADS-CFT correspondence provided concrete mathematical evidence for this idea in 1997. In his framework, a gravitational theory in a five-dimensional anti-de Sitter space is exactly equivalent to a conformal field theory on its four-dimensional boundary. This duality has been enormously fruitful, providing tools to study strongly coupled quantum systems using gravity, and vice versa. If the holographic principle is correct, then the singularity at the center of a black hole might not be a place where physics ends. Instead, all the physics of the interior might be faithfully encoded on the two-dimensional event horizon. The three-dimensional interior, with all its drama, might be a projection, a holographic image cast by the boundary. A spinning black hole does not merely curve spacetime, it drags around like a spinning ball submerged in honey. This frame-dragging effect, predicted by Lentz and Thüring in 1918, has been measured near Earth by Gravity Probe B. Near a rapidly spinning black hole, frame dragging creates the ergosphere, a region outside the event horizon. Inside the ergosphere, space-time is dragged so powerfully that nothing can remain stationary. Everything must co-rotate with the black hole. The boundary of the ergosphere touches the event horizon at the poles and bulges outward at the equator. The Penrose process allows energy extraction from the ergosphere. An object enters, splits, and one piece escapes with more energy than the original. Theoretical calculations show that up to 29% of a maximally spinning black hole's mass energy can be extracted this way. The Blandford-Zenajuk process, involving magnetic fields threading the ergosphere, is thought to power the relativistic jets from active galactic nuclei. These jets can extend millions of light-years, containing enormous amounts of energy extracted from the black hole's spin. Frame dragging also affects the accretion disk. The innermost stable orbit for a particle co-rotating with a Kerr black hole can be much closer than for a Schwarzschild black hole. For a maximally spinning black hole, the ISCO can be at the event horizon itself, allowing matter to orbit much closer and radiate much more energy. The region near the event horizon is where quantum effects first become important in the life of a black hole. The Unruh effect, discovered by William Unruh in 1976, provides a useful analogy. An observer accelerating through empty space will detect thermal radiation that a non-accelerating observer does not see. The temperature of this radiation is proportional to the acceleration, analogous to the Hawking temperature being proportional to the surface gravity. Hawking radiation and the Unruh effects are deeply related. Both arise from the fact that the definition of particles depends on the observer. What one observer calls empty vacuum, another observer, in a different state of motion, calls a thermal bath of particles. This observer dependence of particle content is one of the most profound results of quantum field theory in curved spacetime. Near the horizon, the vacuum state as defined by a freely falling observer differs from the vacuum as defined by a stationary observer far away. The Hawking radiation seen by the distant observer is invisible to the freely falling observer, who sees only empty vacuum. This seeming contradiction is resolved by the fact that different observers, in different states of motion, have different notions of what a particle is. At the center of nearly every large galaxy sits a supermassive black hole with a mass ranging from millions to billions of solar masses. Our own Milky Way harbors Sagittarius A star, a relatively modest 4 million solar masses. The largest known supermassive black holes, like TORM 618, exceed 40 billion solar masses. How supermassive black holes form is still debated. They may grow from smaller seed black holes through accretion and mergers over billions of years. Alternatively, some may have formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar stage entirely. The relationship between a supermassive black hole and its host galaxy is intimate. The mass of the black hole correlates tightly with the mass and velocity dispersion of the galaxy's central bulge. This M-sigma relation suggests that black holes and galaxies co-evolve, influencing each other's growth through feedback processes. When supermassive black holes actively accrete matter, they become active galactic nuclei, or quasars, among the most luminous objects in the universe. A single quasar can outshine its entire host galaxy by a factor of 1,000, powered by the gravitational energy of infalling matter. The most distant quasars observed are seen as they were less than a billion years after the Big Bang, their light having travelled for over 13 billion years. Not all black holes form from collapsing stars. In the very early universe, density fluctuations may have created primordial black holes. Primordial black holes could range from the mass of an asteroid to thousands of solar masses. If small enough, primordial black holes would have been emitting Hawking radiation throughout the history of the universe. Those with a mass of about 10 to the 12 kilograms would be evaporating right now, potentially producing detectable gamma rays. No confirmed detection of such evaporation has been made, placing limits on the abundance of primordial black holes in this mass range. Some physicists have proposed that primordial black holes in the asteroid mass range could account for some or all of the dark matter in the universe. This remains a topic of active research, with gravitational microlensing surveys placing increasingly tight constraints. At the other extreme, quantum mechanics may allow for virtual black holes at the Planck scale, fluctuations in the quantum foam of spacetime. These would exist for only a Planck time before evaporating, but they might influence physics at the most fundamental level. The study of black holes across all scales, from the Planck length to billions of solar masses, remains one of the richest areas of physics. We have traveled a long way tonight, from the calm orbits far from the black hole to the very edge of what physics can describe. We watched the stars warp and bend around the black hole's immense gravity. We felt time slow as we approached the event horizon, our clocks stretching like warm glass under the weight of curved space-time. We crossed the horizon, that invisible boundary, and found that nothing dramatic happened at the moment of crossing. Inside, we discovered that space and time have traded their roles, and the singularity awaits not as a place but as a moment in our future. We explored the deepest puzzles of modern physics, from the information paradox to the firewall debate. And we arrived at the singularity, where our theories dissolve into questions. These questions are not signs of failure, they are invitations to discovery. Every great advance in physics has come from finding the edge of existing knowledge and asking what lies beyond. Newton's gravity was the edge until Einstein pushed beyond it. Einstein's gravity is the edge now, and someone will push beyond it. The singularity at the center of a black hole is perhaps the most important edge in all of physics. Beyond it lies a new understanding of space-time, of gravity, of the quantum structure of reality. We do not know what we will find, but the search is beautiful. The universe contains objects of extraordinary power and mystery. Black holes are among the most extreme, places where gravity bends space-time to its limit and beyond. Einstein's equations predicted them over a century ago. Schwarzschild found the first solution in 1916. Oppenheimer and Snyder showed how they form in 1939. Kerr described spinning black holes in 1963. Penrose proved that singularities are inevitable in 1965 and was awarded the Nobel Prize in 2020. Hawking showed that black holes radiate in 1974, connecting gravity to quantum mechanics in a profound new way. The Event Horizon Telescope captured the first image of a black hole in 2019, confirming what mathematics had predicted. LIGO heard the ripples of merging black holes in 2015, opening a new window on the cosmos. And at the center of each black hole, a mystery waits. A singularity, a breakdown, a question mark written in the geometry of space-time. What is at the bottom of a black hole? We do not yet know. But the question itself is one of the most beautiful in all of science. Let that question rest gently in your mind as you drift towards sleep. The universe is vast and strange and full of wonders. Black holes are among the strangest and most wonderful. They bend time, swallow light, and hide singularities behind horizons of silence. And they wait, patient and eternal, at the hearts of galaxies and the edges of our understanding. Rest now. The mathematics hums softly in the dark. Space-time curves gently around you. The black hole keeps its secrets, and the universe keeps its quiet beauty. Good night. LIGO consists of two identical detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by over 3,000 kilometers. Each detector uses laser interferometry, splitting a laser beam into two beams that travel down perpendicular arms 4 kilometers long. The beams bounce off mirrors at the ends of the arms and recombine. When the arms are the same length, the beams cancel perfectly. A pulsing gravitational wave stretches one arm and compresses the other, creating a tiny mismatch that the laser can detect. The sensitivity required is staggering. LIGO detects changes in arm length of about 10 to the minus 19 meters. That is 1/10,000th the diameter of a proton, or roughly 100 millionth the size of an atom. To achieve this, LIGO must isolate its mirrors from every source of vibration, traffic, ocean waves, earthquakes, even the thermal motion of atoms in the mirror coatings. The mirrors hang from quadruple pendulum suspensions designed to filter out vibrations at the frequencies of interest. The laser power inside the arms is boosted to hundreds of kilowatts using optical resonators. The first detection, designated GW15914, matched a template for two black holes of about 36 and 29 solar masses merging to form a 62 solar mass black hole. The missing 3 solar masses were radiated away as gravitational wave energy in a fraction of a second. The peak luminosity of this event, measured in gravitational waves, was about 3.6 times 10 to the 49 watts. For a brief moment, this single merger was emitting more energy than all the stars in the observable universe combined. The temperature of a Schwarzschild black hole is given by a beautifully simple formula involving only the black hole's mass. T equals h bar c cubed divided by 8 pi g m kb, where h bar is Planck's reduced constant, c the speed of light, g Newton's constant, m the mass, and kb Boltzmann's constant. This formula elegantly combines all 4 fundamental constants of nature with the single physical parameter, mass. For a solar mass black hole, this gives a temperature of about 60 billionths of a Kelvin. The cosmic microwave background radiation has a temperature of about 2.7 Kelvin, vastly hotter than any astrophysical black hole. This means every black hole currently in existence is absorbing more energy from the CMB than it emits through Hawking radiation. Only after the universe cools below the Hawking temperature of a given black hole will it begin to lose mass. The entropy of a black hole is proportional to its horizon area measured in Planck units. A solar mass black hole has an entropy of about 10 to the 77, dwarfing the entropy of the star that formed it. This enormous entropy suggests that black holes have a vast number of internal microstates, even though the no-hair theorem says they look identical from outside. Counting these microstates from first principles is one of the key challenges for any candidate theory of quantum gravity. In 1996, Andrew Strömger and Kumran Vafa achieved this for a special class of black holes in string theory, matching the Bekenstein-Hawking formula exactly. This was a major triumph for string theory, providing the first microscopic derivation of black hole entropy. The idea of a wormhole, a tunnel through space-time connecting distant points, has captivated physicists and the public alike. Einstein and Nathan Rosen first described the Einstein-Rosen bridge in 1935, a feature of the Schwarzschild solution connecting 2 separate regions of spacetime. However, the Einstein-Rosen bridge is not traversable. It pinches off faster than any signal can cross it. In 1988, Kip Thorne and his collaborators explored whether traversable wormholes are possible within general relativity. They found that a traversable wormhole requires exotic matter with negative energy density to keep it open. The Casimir effect, a quantum phenomenon between closely spaced plates, produces a region of negative energy density. But the amount of negative energy needed for a traversable wormhole is enormous, far beyond anything currently achievable. The ER equals EPR conjecture by Susskind and Maldacena proposes a deep connection between wormholes and quantum entanglement. In this picture, every pair of entangled particles is connected by a tiny, non-traversable wormhole. This would mean that the fabric of space-time is woven from quantum entanglement, a breathtaking idea if true. Tidal forces near a black hole are described mathematically by the Riemann curvature tensor. The Riemann tensor measures how nearby geodesics deviate from each other, which is the fundamental expression of gravity in general relativity. For a Schwarzschild black hole, the tidal stretching force on a body of length L at a distance r from the center is proportional to L times m over r cubed. This inverse cube dependence means that tidal forces grow much more rapidly than the gravitational attraction itself, which falls off as 1 over r squared. For a stellar mass black hole of 10 solar masses, the tidal force at the event horizon would stretch a human body with a force of about 100 billion newtons per meter. No material can withstand such forces. The body would be torn apart long before reaching the horizon. But for a supermassive black hole of 1 billion solar masses, the tidal force at the horizon is only about 10 newtons per meter, roughly the weight of a small book. This is why science fiction scenarios involving astronauts crossing the event horizon of a supermassive black hole are physically plausible. The lethal tidal forces would come later, as the astronaut fell deeper inside, but the crossing itself would be gentle. The Penrose process for extracting energy from a spinning black hole is one of the most elegant results in black hole physics. Inside the ergosphere of a Kerr black hole, the energy of a particle as measured at infinity can be negative. If an object enters the ergosphere and splits into two pieces, with one piece having negative energy falling into the black hole, the other piece escapes with more energy than the original. The black hole loses angular momentum and mass equal to the negative energy absorbed. The maximum efficiency of the Penrose process depends on the spin of the black hole. For a maximally spinning Kerr black hole, up to 20.7% of the rest mass of the infalling object can be converted to energy. This is far more efficient than nuclear fusion, which converts less than 1% of rest mass to energy. The superradiance phenomenon, closely related to the Penrose process, allows waves to be amplified by a rotating black hole. A wave scattering off a Kerr black hole can emerge with more energy than it had going in, extracting rotational energy from the black hole. In 2020, researchers at the University of Glasgow demonstrated acoustic superradiance in a laboratory analog using a rotating water vortex. The journey is ending now. We have descended as far as physics currently allows. Behind us lies the event horizon, a boundary we crossed but cannot return through. Ahead lies the singularity, where our theories end and new physics must begin. Between those 2 points, every law of physics we know is tested to its absolute limit. General relativity predicts the curvature. Quantum mechanics demands the particles. Thermodynamics counts the entropy. And at the center, all three meet and disagree, creating a puzzle that may take generations to solve. What is at the bottom of a black hole? Perhaps a singularity, perhaps a bounce, perhaps a doorway. Perhaps something we cannot yet imagine, something that will require entirely new mathematics and entirely new physics. For now, the mystery remains, and there is a deep peace in sitting with mystery. Not every question needs an immediate answer. Some questions are worth holding gently, like a candle in the dark. The black hole holds its secrets, the universe hums its quiet equations, and you are here, resting at the edge of the known. Let the curvature of space-time carry you gently into sleep tonight. The mathematics will still be here in the morning. The black holes will still be waiting. Rest now, surrounded by the quiet beauty of a cosmos that bends time, swallows life,